Hi everyone. Today we're going to be looking at 4.3, which is solving systems of linear equations using the elimination method. To warm up, I want to just look at some of these equations here. We have 36 minus 42 equals negative 6. This can be rewritten vertically as 36 minus 42 over negative 6, like this. We can also rewrite the equation 7x plus 4x equals 11x as 7x plus 4x equals 11x. And so just like how we can do this with expressions, equations can also be added vertically by combining like terms. As long as your equations are lined up by terms, then you can just add straight down. So let's take a look at number 1. So here, if we were to add these up, well, we have 7x plus, we're adding each of these, plus negative 7x. Well, that cancels, that's 0x. Negative 16y plus negative 17y gives us negative 33y. Bring down the equal sign. And we have 441 plus 476 gives us 915. In number 2, if we were to add straight down, 3x plus 12x is equal to 15x. Negative y and positive y cancel out. Bring down your equal sign. 115 plus 50 is 165. And the last one, negative 7x plus 9x gives us positive 2x. Negative 6y and positive 6y cancel out. Bring down your equal sign. 338 plus negative 366 is equal to negative 28. So, part B, what did you notice that happened to one of the variables each time that you added the equations? And why do you think that happened? So, you may have noticed that one of the variables canceled. This is because whenever you have opposite coefficients, or in other words, you have the same number in front where one is positive, one is negative, when adding them, the sum is zero. They zero out or they cancel out. So the sum of opposite coefficients and I'll put in parentheses of like terms is zero. Or in other words, they cancel out. Okay? All right, so in the previous two lessons, we learned how to solve systems by graphing and how to solve systems by the substitution method. The third way that we will study today is how to solve using the elimination method. So let's look at this first example. 2x plus y equals 11 and 3x minus y equals negative 6. So I'm going to go ahead and write that system of equations right here. 2x plus y equals 11. 3x minus y is equal to negative 6. So what we have to do is put them both into standard form, step 1. So this is, remember, ax plus by equals c. So again, these terms have to be aligned vertically. Step 2 is to make sure that you have opposite coefficients. So the same number in front, where one of them is positive and one of them is negative. I noticed that in this example, we do have that. Not in the x term, but in the y term. The top equation has a coefficient of positive 1, and the bottom equation has a coefficient of negative 1. So these are opposite coefficients. So we're ready to eliminate. Step 3 is just to add the equations together, combining like terms. So when we add these up, well, 2x plus 3x is equal to 5x. Y plus negative y cancels out, and that's what we want. Those terms get eliminated, and that's in fact how this method gets its name. And then bring down your equal sign, and 11 plus negative 6 is equal to positive 5. Okay? Step 4, solve the resulting equation. So to solve for x, we're going to divide both sides by 5, and we get x is equal to 1. Step 5, substitute the value you got from step 4 into either of the original equations. And again, I want to underline original equations, similarly to how we did in the substitution method. Anytime that we're substituting back into one of the equations, we want to use the original. And again, the reason why is because if we made an error in manipulating one of the equations, if we plug it into that manipulated equation, it could contain an error, right? Which would cause our solution to be made from an error. So always use the original one because that's what we're given. We know that there's not an error there. Okay, so back to this problem, x equals 1. We're going to go ahead and plug that into either of the original equations. I'm going to choose to plug it into the very first equation, which is 2x plus y equals 11. Solving for y, we get 2 plus y equals 11. Subtracting 2 from both sides, and we get y is equal to 9. Step 6 says to write the solution as an ordered pair. So the ordered pair solution in this case is 1, 9. And then step 7 is to check both of the original equations to make sure that it's true. So we're going to plug in 1 for x and 9 for y into both of the equations and see if they are true equations. So we have 2 times 1 plus 9 equals 11 for the first equation. 2 times 1 is 2 plus 9 equals 11. And 2 plus 9 is indeed equal to 11. And so that one checks out. Let's check the other one. 3x minus y equals negative 6. So 3 times 1 minus 9 is equal to negative 6. Well, 3 times 1 is 3. Minus 9 equals negative 6. And indeed, negative 6 is equal to negative 6. So this checks out as well. So we know that we have solved this correctly. All right, on to the next page. Let's go ahead and try another one. We want to solve this system using the elimination method. So step 1, put the equations in standard form. These equations are already in standard form, so step 1 is already done for us. I'm going to go ahead and rewrite the equations over here in our working space. Step 2, check for opposite coefficients. Do we have the same number in front where one's positive, one's negative? We do. We have it in the y terms. So step 2 is already done too. Step 3, we're just going to add the equations together. 3x plus 4x is 7x. Y plus negative y cancels out. Bring down your equal sign. 19 plus 2 is equal to 21. To solve, we divide both sides by 7. So 21 divided by 7 is equal to 3. Now we have x equals 3. We can plug that into either of the original equations. I'm going to choose the top one. So we have 3 times 3 plus y equals 19. 3 times 3 is 9, plus y equals 19. And subtracting 9 from both sides, we get y is equal to 10. So our solution as an ordered pair is 310. Now we have to check and make sure that that solution works for both of the original equations. So we have 3x plus y is equal to 19, and we have 4x minus y is equal to 2. So I'm going to plug in 3 for x and 10 for y. So in the first equation, 3 times 3 plus 10 is equal to 19. Well, 3 times 3 is 9, plus 10 is equal to 19. And we get 19 is equal to 19. So that works. In the second equation, 4 times 3 minus 10 is equal to 2. 4 times 3 is 12, minus 10 is equal to 2. And 12 minus 10 is equal to 2. So that checks out as well. So we've done this one correctly. Let's take a look at example 3. So let's try to solve this system. So remember, step 1 is to put it in standard form. We've already got that. Step 2 is to check for opposite coefficients. So right now we don't have any opposite coefficients, but how can we get opposite coefficients? I noticed that, well, 3 and 2 are close, but doesn't seem like we can do much with those. I did notice, though, that the y terms are already opposite. So one is positive, one's negative. So I'm wondering, how can I get from the coefficient of the y in the second equation, negative 1, to be negative 5? And the answer is we're going to multiply that whole equation by 5. And notice what happens. If I multiply this whole equation, I'll actually write down here. I'll copy down both equations, just so that I've got a little bit of working space. So minus y equals negative 5. Okay, if I multiply this bottom equation entirely by 5, well, notice what happens. We have to distribute this 5 into every term in this equation. So over here, I'm just going to draw an arrow and multiply this out. Well, 5 times 2x is equal to 10x. 5 times negative y is equal to negative 5y equals and 5 times negative 5 is equal to negative 25. I'm also going to bring over my top equation. I'm not going to do anything to that. I'm just going to bring it over and rewrite it. And notice now that we've multiplied the second equation by 5, we do now have opposite coefficients where one is positive, one's negative, with the same number in front. So we are ready to add. So now when we add these equations up, we get 3x plus 10x equals 13x. 5y and negative 5y cancel out. That's very good. That's what we wanted. And then bring down your equal sign. 12 plus negative 25 is equal to negative 13. Solving this equation by dividing by 13 on both sides, we get x is equal to negative 1. Now here we want to plug into one of the original equations. So I would not plug this into 10x minus 5y equals negative 25, because in case we made an error multiplying by 5, our answer would contain an error. So let's go ahead and plug it into one of the original equations. I'm going to be safe and do the one that we didn't even touch at all. So 3x plus 5y equals 12. So I'm going to plug in negative 1 in for x and solve for y. So 3 times negative 1 is negative 3, plus 5y is equal to 12. Adding 3 to both sides, we get 5y is equal to 15. And dividing both sides by 5, we get y is equal to 3. So the solution to this system of equations is negative 1, 3. Let's go ahead and check our work just real quick. We'll plug into both of the equations. So 3x plus 5y equals 12. In the other original equation, 2x minus y equals negative 5. We'll plug in the coordinates negative 1, 3. So we have 3 times negative 1 plus 5 times 3 in the first equation equals 12. So we have negative 3 plus 15 equals 12. Well, negative 3 plus 15 does equal 12. And so we have 12 equals 12. That is true. In the other equation, we have 2 times negative 1 minus 3 is equal to negative 5. Well, 2 times negative 1 is negative 2. Minus 3 equals negative 5. And negative 2 minus 3 does equal negative 5, so that checks out as well. We've done this one correctly. Okay. Let's get some more practice. So let's go ahead and solve these systems using the elimination method. Number 1, we have opposite coefficients, so we're going to go ahead and just add the equations. Our y terms cancel out. Our x's add up to 3x, x plus 2x. And our constants on the right-hand side, 5 plus 1 is 6. Dividing both sides by 3, we get x is equal to 2. Plugging into one of the original equations, we have, I'll do the first equation. So 2 plus 3y is equal to 5. Subtracting 2 from both sides, we get 3y is equal to 3. And dividing both sides by 3, we get y is equal to 1. So our solution as an xy ordered pair is 2, 1. Number 2. Again, we have opposite coefficients, but now in the x terms. So as we add the equations, the x terms cancel out. 2y plus 3y is equal to 5y. 12 plus 8 is equal to 20. So we have 5y equals 20. Solving, dividing both sides by 5, we have 20 divided by 5 is 4. Plugging into one of the original equations, I'm going to plug into the first equation. 4x plus 2 times 4 equals 12. Well, 2 times 4 is equal to 8. So 4x plus 8 equals 12. Subtracting 8 from both sides, we get 4x is equal to 4. So x must be equal to 1, dividing both sides by 4, right? So our solution is 1, 4. All right. Let's continue. Number 3. Here we have 7x plus 10y equals negative 37 and 3x minus 5y equals 12. Here we do not have opposite coefficients, but I noticed that we have different signs for the y's. So we have one is positive, one's negative. And I also noticed that 10 is a multiple of 5. In fact, it's 5 times 2. So if I multiply the second equation by 2, then that should cancel out our y terms. So I'm just going to rewrite that top equation. 7x plus 10y is equal to negative 37. And then 2 times 3x is 6x. 2 times negative 5y is negative 10y. And 2 times 12 is 24. Now we can add these equations and our y terms cancel. 7x plus 6x is equal to 13x, and negative 37 plus 24 is equal to negative 13. Dividing both sides by 13, and we get x is equal to negative 1. Plugging into either of the original equations, I'm going to choose the second equation this time. So 3 times negative 1 minus 5y is equal to 12. We have negative 3 minus 5y is equal to 12. Adding 3 to both sides, and we get negative 5y is equal to 15. And dividing both sides by negative 5, we get y is equal to negative 3. So we have the solution negative 1, negative 3. All right. On the next one, I notice that the bottom equation, it looks like, well, I know 6 is a multiple of 3, so we can multiply the bottom equation. And I also know that 2 is a multiple of 1. But we also want it to be opposite signs, so we need them to be negative. So let's go ahead and multiply the bottom equation by negative 2 and see what that gets us. The top equation, I'll rewrite, 6x plus 2y is equal to 20. And multiplying the bottom equation by 2, we get negative 6x minus 2y is equal to negative 20. Adding these equations up, something very interesting happens. 6 plus negative 6x cancels. 2y plus negative 2y cancels. 20 plus negative 20 cancels. Everything cancels, so we're left with nothing on both sides of the equation. So 0 equals 0. Now, we always have to ask ourselves, is this a true equation? Does 0 equal 0? Anytime you have a number equals a number. This is true. 0 does equal 0. So because this is true, we have infinitely many solutions. We learned something like this last lesson in 4.2, solving by substitution. And graphically in 4.1, this would look like some two lines that are stacked on top of one another. All right. Let's continue. Number 5. So for number 5, I noticed that, let's see, we can't multiply the top equation. Like I'm looking at the x's. There's nothing we can multiply, not an integer anyway, that we can multiply 2 by to get negative 3, or positive 3, I should say. We could, however, multiply 1 by something to get positive 5. And the answer to that is 5. So I'm going to multiply the bottom equation by 5 and the top equation by nothing. So we have 2x minus 5y is equal to 9. The bottom equation, 5 times negative 3 is negative 15. 5 times 1 is just 5, so 5y. And 5 times negative 7 is negative 35. All right, 2x minus 15x, or 2x plus 15, negative 15x is negative 13x. Negative 5y and positive 5y cancel, and 9 plus negative 35 is negative 26. Dividing both sides by negative 13, we get x is equal to positive 2. Plugging into the original equation, 2x minus 5y is equal to 9. We have 2 times 2 minus 5y equals 9. 2 times 2 is 4. Minus 5y equals 9. Subtracting 4 from both sides, we get negative 5y is equal to 5. And dividing by both sides by negative 5, we get y is equal to negative 1. So the solution to this system as an ordered pair is 2, negative 1. And number 6, this one has an asterisk. To solve this system, you need to multiply both equations by values that give you opposite coefficients. These types of questions are a little bit more difficult. So looking at this, I notice that there's no integer that I can multiply 3 by to get to 8. And likewise, there's nothing that I can multiply by, no integer, that I can multiply 5 by to get to 6. So I have to multiply both of these equations by a number so that we get the same number in front, but opposite signs. So one thing that we could do is find the least common multiple of those coefficients. So the least common multiple for 8 and 3 is 24, or the least common multiple of 6 and 5 is 30. So you can choose to multiply by what gives you that least common multiple. So let's do the y terms. We want to cancel those out. So that means I'm going to multiply I chose the y terms, by the way, because they already have opposite signs, so I'm going to multiply by positive numbers. I'm going to multiply the top equation by 5, because I want that y term to get to negative 30y. And then I'm going to multiply the bottom equation by 6. And let's see what happens here. If I multiply the top equation by 5, well, then I'm left with 40x minus 30y is equal to negative 700. And the bottom equation, I get 18x plus 30y is equal to 120. And this is really good because now we can see that we have opposite coefficients. The same number in front, one's positive, one's negative in the y term. So we can add up these equations. 40x plus 18x gives us 58x. Y terms cancel out. And negative 700 plus positive 120 is negative 580. Dividing both sides by 58, and we get x is equal to negative 10. Now I'm going to plug this back into one of the original equations. I'm going to plug it into the top one. So 8 times negative 10 minus 6y is equal to negative 140. 8 times negative 10 is negative 80. Minus 6y equals negative 140. Adding 80 to both sides, we get negative 6y is equal to negative 60. And then dividing both sides by negative 6, we get y is equal to positive 10. So our solution as an ordered pair, negative 10, 10. All right, let's continue. Now we're going to start looking at modeling. So example 4, James works in a department store selling sports equipment. Volleyballs cost $29 each, and knee pads cost $14 per pair. Last Sunday, James sold 28 items. His total sales were $647. And the question that we need to answer is how many volleyballs and knee pads did James sell? 4a says, set up a system of linear equations that model this situation. So first, anytime you have modeling, we have to define our variables. So let's say let v be the number of volleyballs sold. And then we'll say let k be the number of knee pads sold. And we always want to be specific. Don't just say let v be the volleyballs. That doesn't tell us much about the volleyballs. Are we saying the color of the volleyballs, the size of the volleyballs? We want to be specific. It's the number of volleyballs. So be as specific as you can when defining your variables. To set up a system of linear equations, we can consider how many of each that they sold and then for how much they sold. Okay? So let's take a look at the total that they made in sales. So we know that volleyballs cost $29 each, so we can say that they made $29 per volleyball, so times the number of volleyballs. For knee pads, we know that they made 14 per pair of knee pads. And then in total, if we add up all of their sales, that's going to be total 647. We also know the number of items they sold, so the number of volleyballs sold plus the number of knee pads sold is equal to 28. So we can set up these two equations. 29v plus 14k equals 647, and v plus k equals 28. To solve this system, I'm just going to rewrite it down here in part B. And we want to use this, we want to solve this using the elimination method. So 29v plus 14k is equal to 647, and v plus k is equal to 28. In order to solve this, I'm going to multiply the bottom equation by negative 14. Now I'm choosing negative 14 because I want those k's to cancel out. I also am multiplying by negative because I want them to be opposite signs. So when I multiply this by negative 14, here I'll bring over the top equation, 29v plus 14k equals 647. When I multiply this, I get negative 14v, I get minus 14k, and I get is equal to negative 392. When I add up these equations, my k's cancel out, my v's become positive 15v is equal to 255. Dividing both sides by 15, we get V is equal to 17. Okay, now we can plug this back into one of the original equations. One of them looks a whole lot easier to me than the other, and that's the second equation. So I'm going to plug that into the second equation. V plus K equals 28. So 17 plus K is equal to 28. Subtracting 17 from both sides, and we get K is equal to 11. Part C, does it make sense to express your solution as an ordered pair when using a system as a mathematical model? Why or why not? In this case, does it make sense? The answer is no, because these equations don't represent a function with a dependent and independent variable. So let's go ahead and write that. No, because the equations do not represent a function with dependent and independent variables. Or in other words, the number of knee pads sold does not depend on the number of volleyballs sold, and vice versa. The number of volleyballs sold does not depend on the number of knee pads sold. They are both independent of one another. So let's go ahead and answer the question. James sold 17 volleyballs and 11 knee pads. Or it should be pairs of knee pads. All right, on to the next page. Nita's archaeology club visited a state park to view some ancient rock drawings. 2 adults and 5 students in one van paid $77 for the visit. 2 adults and 7 students in a second van paid $95. The question we want to answer, what were the entry prices for a student and an adult? So to set up the system, again, first we want to define our variables. So let's say let A be the adult ticket price. And then we'll say let S be the student ticket price. And the reason why we choose these to be our variables is because that's what we're looking for. We're looking for the entry prices, the ticket price, for both a student and an adult. Okay. So we know that in the first van, we had 2 adults and 5 students, all paid $77. So if we add up the total spent for that first first van, then we would get $77. In the second van, we have 2 adults and 7 students, paid a total of $95. So in order to solve this, I noticed that for our A's, we have the same number in front, but both of them are positive. So we can multiply one of the equations, it doesn't matter which, I'm going to multiply the second equation, by -1. And that's going to flip all of the signs in the equation. Let's go ahead and rewrite both of these. Top equation doesn't change. 2a plus 5s is equal to 77. The bottom equation becomes -2a minus 7s is equal to -95. And now we can see that as we add the equations, the a's cancel. 5s minus 7s is equal to -2s. And 77 minus 95 or plus -95 is -18. Dividing both sides by -2, we have s is equal to +9. Plugging into one of the original equations, 2a, I'm going to choose the top one, plus 5 times 9 is equal to 77. 2a plus 45 is equal to 77. Subtracting 45 from both sides, we get 2a is equal to 32. And then dividing both sides by 2, we get a is equal to 16. All right, so let's go ahead and answer the question. I've got some space over here. So the entry prices were $16 per adult ticket and $9 per student ticket. All right. So do make sure that you actually answer the question. I see a lot of students just write their solution as an ordered pair. Remember to actually answer the question that they're asking. So if they're asking for what are the entry prices, don't just say 16 comma 9. Tell me that the adult tickets were $16 and the student tickets were $9. All right. Example 6. Here we want to look at each of these systems of linear equations and determine which method we want to use to solve them. So part A. In this case, I noticed that we have a y equals equation. So we could just take this expression that y is equal to and substitute it in for y in the other equation. So I would choose the substitution method. And my explanation is because in the second equation, the y is isolated and can easily substitute into the first equation. And we do not have to solve these systems, just determining which method you want to use and your explanation, your justification. For letter B, I noticed that both of these are in standard form. None of them have a y equals or x equals equation, so I would choose elimination. And explanation because both equations are in standard form. Okay. And last but not least, letter C. I noticed that yes, both of these equations are in standard form, so we could use the elimination method, but I also noticed that the coefficient of x in the second equation is 1. So this is one step away from being an x equals equation. So this is could very possibly be a pretty easy substitution problem. So I would say either of the methods are acceptable. You might say elimination because they're both in standard form. But substitution was the first one that came to my mind, so I'm going to say substitution. But put what you think and put in your justification. So my justification for substitution is that adding 4y to both sides of the second equation would isolate x, which then could easily substitute into the first equation. So again, whichever method you saw first or whichever you think is easier, you can circle that and then provide your justification. All right. Last page, let's try example 7. So this is a modeling example. Alana is planning her parents' 25th wedding anniversary dinner party. She spoke to 2 different restaurants, La Casa and Hastings Hall, and graphed the cost of each of them on the graph below. A. Write a system of linear equations that represents this graph. So in order to write a system, we need to come up with the equations. Let's start with La Casa. So I noticed that from the graph, this crosses the y-axis at, well, it looks like up here is 2,000. So then halfway must be 1,000. So it looks like every 2 increments is 1,000. So that means up here must be 3,000, then 4,000, or every 1 increment would be 500. Okay. So I know that the y-intercept of the line graphed for La Casa is 1,000. To find the slope, I need 2 points. So I'm going to choose the y-intercept. So I'm going to just go ahead and write that over here, 0, 1,000. But then I'm also going to choose, let's do this point right over here, which has the coordinates 20, 2,000. So again, we're looking for points that cross the grid lines really nicely. To find the slope, we're going to use our slope formula. So m equals y2 minus y1 over x2 minus x1. So we have 2,000 minus 1,000 over 20 minus 0. This reduces to 1,000 over 20, which evaluates to 50. So that tells me that my slope is 50, or the equation in slope-intercept form is y equals 50x plus 1,000 for La Casa. For Hastings Hall, I'm looking at the y-intercept, so it looks like that one is over here. So actually, let's go ahead and write that. So 0, 2,000. So the y-intercept is 2,000. For the slope, we need another point. Looks like the next best one might be right around here. We can use that one. So that's at 43,000. So let's find the slope. M is equal to y2 minus y1. So 3,000 minus 2,000 over x2 minus x1, 40 minus 0. And this is equal to 1,000 over 40, which evaluates to 25. So the equation in slope-intercept form of Hastings Hall is y equals 25x plus 2,000. So let's go ahead and write both of those equations as a system. So y equals 50x plus 1,000 for La Casa, and y equals 25x plus 2,000 for Hastings Hall. Part B, solve the system of equations using substitution or elimination. Well, I notice that both of these are solved for y, so I can just set these expressions equal to one another. So 50x plus 1,000 is equal to 25x plus 2,000. Solving for x, I'm going to subtract 25x from both sides. And on the right-hand side, they cancel, so we're left with 25x plus 1,000 is equal to 2,000. Subtracting 1,000 from both sides, we get 25x is equal to 1,000. And dividing both sides by 25, we get x is equal to 40. Plugging in our solution of 40 in for x in one of the other equations, we'll choose the top equation. So we have y is equal to 50 times 40 plus 1,000. So we get y is equal to 2,000 plus 1,000. So then y must be equal to 3,000. So our solution as an ordered pair is 40, 3,000. Part C. Which restaurant should Alana choose if she only plans on 20 guests attending, and why? So let's take a look. At the graph, we can see at number of guests, x-axis, where it equals 20, which one has a lesser cost, or which one is cheaper. So over here, if we look at 20, the lesser of the two is this green line for La Casa. So La Casa is going to be less expensive. So Alana should choose La Casa because it is less expensive. Which restaurant should Alana choose if she plans on 40 guests attending, and why? At this point, let's take a look at the graph. At 40 guests, it looks like they are equal. In fact, these are where the lines cross. We verified that this is the solution to the system when we solved this using the substitution method. At 40 guests, they're going to have the same cost of $3,000. So it's totally up to Alana. She can choose either. So either restaurant. Since they both will charge the same amount $3,000. All right. So this concludes our notes on solving systems of linear equations using the elimination method. We're going to get a lot of practice in class, so we'll see you tomorrow. Have a great day, everybody. Goodbye.